Hello everyone, I am Himanshu Vasnani from Department of Mechanical Engineering. I am here to discuss with you on the subject non-destructive evaluation and testing. The subject code is ME419, unit number 3, lecture number 19 in the series, and today's topic are piezoelectric transducers, radiated fields of ultrasonic transducers, and transducer beam spread in ultrasonic testing. We have been discussing about ultrasonic testing in the past lectures also. So we will discuss these topics in our coming lecture. So learning objective for today will be to provide the students with a basic understanding of piezoelectric transducers, radiated fields of ultrasonic transducers, transducers beam spread in ultrasonic testing, and to know about various variables affecting radiated fields of ultrasonic transducers. Learning outcome will be students will have understanding of piezoelectric transducers, related fields of ultrasonic transducers, transducers being spread in ultrasonic testing, and students will understand various variables affecting related fields of ultrasonic transducers. Let's start with today's lecture. So we have been discussing about transducers in our previous lectures also, and we have discussed about various types of transducers like contact transducers, immersion transducers, angle beam transducers, and there were different type of delay time transducers. So there were different types of transducers like delay time transducers. Each transducers have their own style of working. Okay, like in contact, there was a contact between the workpiece and the transducers, whereas in immersion transducer there was no contact. Okay, so every transducer has its own style of working. So now we are studying about piezoelectric transducers. Okay, so let's start with it. The conversion of electric pulses to mechanical vibrations and the conversion of returned mechanical vibrations back into the electrical energy is the basis of ultrasonic testing. We have discussed this earlier also about this basic principle of ultrasonic testing, that it is the conversion of electric pulses to mechanical vibration and the conversion of in return mechanical vibrations back into the electrical energy in the form of signals. Okay, is the basis of ultrasonic testing. Okay, we have seen in the right side on the diagram also, you can see if the electric current is off. Okay, you have electrical source, then you have seen that how this works, and there is change in the dimensions when the electric current is on. So here, when we discuss more about it, that the this conversion of is done by the transducer using a piece of piezoelectric material. These conversions, like from electric pulses to mechanical vibrations, and then from mechanical vibrations back into electrical energy, to and you see the pulses. This conversion is done by the transducer using a piece of piezoelectric material. Now the term is coming, piezoelectric material. That is a polarized material. This is about piezoelectric. It is a polarized material having some parts of molecule positively charged while the other part of the molecule are negatively charged. Now, this conversion is done by the transducer using a piece of piezoelectric material with electrodes attached to the two of its opposite faces. So when you apply an electric field, okay, when electric field is applied across the material, the polarized molecules will align themselves with the electric field, causing the material to change the dimensions. You can see this in the diagram on the right hand side, how you can see the dimensions are being changed in this. Okay, when the electric current is on. Okay. Uh, in addition, a permanently polarized material such as quartz or barium titanate will produce an electric field. Okay, a permanently polarized material such as quartz or barium titanate, these are the two polarized materials, will produce an electric field when the material changes dimensions as a result of an imposed mechanical force. I repeat, whenever you apply the electric field across the material, what happens? The polarized materials, or the polarized molecules, the polarized molecules will align themselves with the electric field, and it leads to the change in the dimensions of the material. Okay, it will the electric field causes the material to change dimensions. Now, what happens in addition, a permanently polarized material such as quartz or barium titanate will produce an electric field when the material changes dimensions as a result of an imposed mechanical force. This phenomenon is known as piezoelectric effect. Okay. Now, the active element of most acoustic transducers used today is a piezoelectric ceramic, which can cut in various ways to produce different wave molecules. Okay, they usually use a piezoelectric ceramic. Okay, which can be cut in various ways. I can this term also into piezoelectric ceramic. You can see in this diagram also in the first slide. Okay, a large piezoelectric ceramic element can be seen in the image of a section low frequency transducer. And the most commonly employed ceramic for making transducer is lead zirconate titanate. You should remember this material, that is the most commonly used ceramic for making transducers. Ceramic for making transducers is lead zirconate titanate. This is an important material. The thickness of the active element is determined by the desired frequency of the transducer. The thickness of the active element is determined by the desired frequency. Okay, desired frequency of the transducer. So a thin wafer element vibrates with a wavelength that is twice its thickness. Okay, it will vibrate with a wavelength twice its thickness. Therefore, a piezoelectric crystals are cut to a thickness that is half the radiated wavelength. The higher the frequency of the transducer, the thinner the active element is. Okay. Now, before this, I just want to explain this principle once again, because this principle will be used in the later on. Like this, when an electric field is applied across the material, the polarized molecules align themselves with the electric field, causing the material to change the dimensions. You can see this in the diagram. So, in addition, a permanently polarized material such as quartz, quartz is used of barium titanate. Okay, this will produce an electric field when the material changes dimensions as a result of an imposed mechanical force. So, this phenomenon is known as piezoelectric effect. Remember this effect. It will be helpful to discuss in the coming slides. Okay. The characteristics of a piezoelectric transducers. Okay. Now you can see that the function of a transducer is to convert electric signals into mechanical vibrations. Now this function is done when it is in transmit mode, right? And when you talk about you can say uh, and mechanical vibrations into electrical signals when you're in the receive mode. So here the transducer is acting in two modes, one in transmit mode and one in receive mode. The function of the transducer is to convert signals into mechanical vibrations when it is in transmit mode, and mechanical vibrations into electrical signals when it is in receiver mode. So many factors, including like material, mechanical and electrical constructions, and the external mechanical and electrical load conditions, these influence the behavior of a transducer. Well, the transducers are of various types like contact, immersion, delay time. You can say that angle transducers, angle beam transducers. These are, but uh, factors. There are many factors like material, uh, like electrical and mechanical construction, or external electrical and mechanical load conditions. These influence the behavior of a transducer. So in that case, these are important. Okay, in that case, these are important. So now they influence the behavior of the transducer. Now the sorry, a cutaway of you can see in the diagram also it is shown that a cutaway of a typical contact transducer. Now if we just take an example, of a contact transducer is shown in the figure. To get as much energy out of the transducer as possible, an impedance matching layer is placed between the active element and the face of the transducer. Okay, now our purpose is to get as much energy as possible. So to get as much energy out of the transducer as possible, an impedance matching layer that is placed between the active element and the face of the transducer. The face. Okay. Then optimal impedance matching is achieved by sizing the matching layer so that its thickness is 1/4 of the desired value. Okay. They, first of all, to get the maximum energy, we use an impedance matching layer. Okay. Then to achieve, or you can say for optimal impedance matching, what to achieve this is achieved by sizing the matching layer so that its thickness is 1/4 of the desired wavelength. This keeps waves that are reflected within the matching layer in phase when they exit the layer. Okay, this the what we did by sizing the matching layer so that its thickness is 1/4 of the desired wavelength. This what we did is this is keeping the waves that are reflected within the matching layer in phase, within the matching layer in phase when they exit the layer. Okay, like for contact transducers, the matching layer is made from the material that has acoustical impedance between the active element and steel. Okay, uh, immersion transducer. Now it's talking about second transducer. Immersion transducers have a matching layer with acoustical impedance between the active element and water. Now, because water is used when using immersion transducers, okay, but for contact transducers, it is in direct contact with the material. So, the matching layer is made from a material that has acoustic impedance between active element and steel. This is in case of contact transducers. But when we talk about immersion transducer, okay, the matching layer is made with acoustic impedance between the active element and water. Okay. Also, they say that the contact transducers incorporate a wear plate to protect the matching layer and the active element from scratching. We since we also studied before also for contact transducer that we have to save the upper layer from getting weird or from scratching. So here also they incorporate a wear plate that protects the matching layer. Okay, that protects the matching layer and the active element from sketching. So here this holds its importance. Now the backing plate. Now this is another term that is you are understanding after matching layer. Okay. Now the backing material supporting the crystal has a great influence on the damping characteristics of a transducer. Okay. Now talking about the damping characteristics. So there is another term that is coming in front of you after the matching layer. That is the backing material. So the backing material supporting the crystal has a great influence on the damping characteristics of a transducer. Using a backing material with an impedance similar to that of active element will produce the most damping. Using a damping material with an impedance that is similar to that of the active element will produce most of the effective damping. Such a transducer will have a wider resulting in higher sensitivity. Such a transducer will have a wider bandwidth resulting in higher sensitivity and higher resolution. Now, if we achieve such kind of wider bandwidth, which will give you higher sensitivity and higher resolution, then what it will give you? It will give you the ability to locate defects near the surface or in close proximity in the material. Okay, so here when the transducer using such kind of, you can say, backing material, okay, so what it will do, it will give you a wider bandwidth, and this wider bandwidth will give you higher sensitivity and resolution, which means that you will have the ability to locate defects near the surface or in close proximity of the in the material. So this is good. So as the mismatch in impedance between the active element and the backing material increases, material penetration increases, but transducer sensitivity reduces. But if there is a mismatch in impedance, okay, now if there is mismatch in the impedance between the active element and the backing material, you can see in the diagram, active element and backing material increases. There's a mismatch in impedance. If it is increasing, then the material penetration will increase, but transducer sensitivity will decrease. Okay, if sensitivity is decreased, then the ability will be affected to locate defects. Okay, it will get affected. The bandwidth here refers to the range of frequencies associated with the transducer. Okay, the bandwidth that we are discussing here, it refers to the range of frequencies. It refers to the range of frequencies associated with the transducer. Okay, the frequency noted on a transducer is the central frequency. The frequency that we are noting here on a transducer is the central frequency and depends primarily on a backing material. Now you can see the importance of backing material. Okay, every you can say element in a transducer like matching layer, like backing material, they all have an importance. If they all are in proper impedance, then the sensitivity is okay, is good, resolution is okay. Okay, so we are say that the frequency noted on a transducer is the central frequency and depends primarily on the backing material. Now, highly damped transducers will respond to frequencies. Okay, and highly damped transducers will respond to frequencies above and below the central frequency. Respond to frequencies above and below the central frequency. The broad frequency range provides a transducer with high resolving power. Less damped transducers will exhibit a narrower frequency range and poorer resolving power, but greater penetration. We also studied in the previous slide also. If you can see, if there is a mismatch in the impedance, so what will happen? The material penetration will increase, but transducer sensitivity is reduced. Okay, mismatch in impedance between the active element and the backing material. Here, material penetration increasing, but transducer sensitivity is reducing. Here, it is saying that less damped transducer, what it will do, it will exhibit a narrower frequency range and poorer resolving power, but greater penetration. Okay, so we should understand that uh, highly damped transducers, what happens, they do, they respond to frequencies above and below the central frequency. So if we have broad frequency, high resolving power we will have. If we have less damped transducers, so it will give you a narrow frequency range, so it will give you a resolving power. Okay, it will give you a low resolving power, but it will give you greater penetration. Okay, the central frequency, greater penetration. After that, the central frequency will also define the capabilities of a transducer, like lower frequency of this megahertz, like 0.5 megahertz to 2.25 megahertz, provide greater energy and the penetration in the material. This is one thing. While the higher frequency crystals like 15 megahertz to 25 megahertz provide reduced penetration but greater sensitivities to small discontinuities. So you can understand that each frequency has its own capability, has its own, you can say, USP. If you have lower frequency, then you will have more penetration in the material. Okay, if there is less frequency, sorry, if you have less frequency, then more penetration in the material. If you have high frequency, then you have less penetration, but sensitivity is good for defects and discontinuities, which we automatically require because our purpose for ultrasound testing is to find out the discontinuities. Okay, so for this we require high frequency crystals. Okay, so let's go further after this high frequency crystals. Now, radiated fields of ultrasonic transducers. Now, this is an also another important topic for this. Okay, let's start with this. The sound that emanates from a piezoelectric transducers does not originate from a point, but instead originates from most of the surface of the piezoelectric element. Okay, the sound field from a typical piezoelectric transducer you can see in the figure. Okay, in the figure you can, I'll tell you, where lighter colors indicating higher intensity. Okay, since the ultrasound originates from a number of points along the transducer face, the the ultrasound intensity along the beam is affected by constructive and destructive wave interference as discussed. Okay, so this wave interference this leads to extensive fluctuations in the sound intensity near the source and is known as near field. Okay, now this is a new term that you are facing, that is the near field. What happens in this? When the wave interference, okay, when they lead to extensive fluctuation in the sound intensity while testing near the source, it is called as near field. Okay, and because of acoustic variation within a near field, it can be difficult to accurately evaluate flaws in the material when they are positioned within this area. Okay, when you have extensive fluctuation in the sound intensity near the source, what happens that during that time, during that near field, because of acoustic variation within the near field, the you can say evaluation of flaws or discontinuities or finding of discontinuity is difficult. You can say the accuracy gets hammered. It is difficult to find out that in materials. Okay, when they are positioned within this area, so we have to be careful with that. So the pressure waves combine to form a relatively uniform front at the end of the near field. So the area beyond the near field where the ultrasonics beam is more uniform is called as far field. Now there are two fields that I are discussing in this. That is the one was the near field that was discussed in this slide, and then there is the far field. Okay, now near field has its own that the detection of flaws is you can say um, is quite difficult. But if you talk about the far field, okay, now we are discussing about that. That the transition between the near field and the far field occurs at a distance and sometimes referred to as natural focus of a flat or unfocused transducers. So spherical or cylindrical focusing changes the structure of a transducer field by pulling the point near the transducer. Okay, what happens? The area just beyond the near field is where the sound wave is well behaved and at its maximum strength. Therefore, optimal detection results will be obtained when the flaw occurs in this area. Okay, so you can remember these two things: near field and far field. Okay, so you can say the area beyond the near field where the ultrasonic beam is more uniform, then called as a far field. Okay, and you can say this near field, you can say that the area you can say which leads to extensive fluctuation in the sound intensity near the source. It is called as a near field. So in the near field, it is difficult to accurately evaluate flaws in the material. Okay, when they are in the near field, right? But if you go to the far field, okay, here the ultrasonic beams are more uniform. Okay, so it is good. So for a round transducer, often referred to as you can say piston source transducer because it is a round shape. The near field distance can be found as n is equals to d square f upon 4v. Now here the d stands for transducer diameter, f stands for transducer frequency, and v stands for sound longitudinal velocity in the medium through which the waves are transmitted. So you can find out the near field distance with this formula d square f upon 4v. Now transducer beam spread. Okay. Now this is also a kind of a topic that we should understand, that you can see in the diagram you have beam spread is there in the red, and then there is beam divergence. There are two terms that you are seeing in this diagram also. So through this we can see that as the sound wave this exit the near field, okay, and propagate through the material, the sound beam continuously spreads out. I repeat, as the sound wave this exits the near field and propagates through the material, the sound beam continuously spreads out. This phenomenon, when the sound beams are continuously spreading out, okay, this phenomenon is referred to as beam spread. It is called as beam spread. You can see in the diagram. It is called as beam spread. But sometimes it is referred to as beam divergence or ultrasonic diffraction. Okay, I repeat regarding transducer beam spread. See, when the sound waves exits the near field and propagate through the material, the sound beams continuously spread out. So this phenomenon is usually referred to as beam spread. But sometimes it is also referred to as beam divergence or ultrasonic distraction. Ultrasonic diffraction. Okay, you can remember this thing. It should be noted that there is actually a difference where beam spread and beam divergence. You can see in the diagram also these two terms are written and shown in the diagram also. Okay, like the when the sound beam is spreading out, you can tell that as beam spread. But when there is a difference between beam divergence also with that. Okay, we can also sometimes you can also sometimes refer this as beam divergence also. But there is a difference. Beam spread is the measure of the whole angle from side to side of the beam in the far field. I repeat, this beam spread is actually the measure of the whole angle from side to side of the beam in the far field. Beam divergence is the measure of the angle from one side of the beam of the sound beam to the central axis of the beam in the far field. You can see in the diagram it's shown that beam divergence is the measure of the angle from one side of the sound beam to the central axis of the beam in far field. Therefore, beam spread is twice the beam divergence. Simple, remember this formula. Beam spread is twice the beam divergence. When you talk about transducer beam spread, okay, beam spread is twice the beam divergence. That is the good thing. Twice the beam spread is twice the beam divergence. So although beam spread must be considered when performing an ultrasonic inspection because this is the main purpose that we are doing. So it is important to note that in the far field or Fraunhofer zone, the maximum sound pressure is always found along the acoustic axis, that is the center line of the transducer. Okay, therefore the strongest reflections are likely to come from the area directly in front of the transducer because the center line, the center line has the maximum sound pressure. So the strongest reflections are like to come from directly in front of the transducer. So beam spread occurs because the vibrating particles of the material through which the wave is traveling do not always transfer all of the energy in the direction of wave propagation. Okay. Now the particles are not directly aligned in the direction of wave propagation. Some of the energy will transferred off an angle. Okay, transferred off at an angle. So in the near field, the constructive and destructive wave interference fill the sound wave with fluctuation. Okay. So at the start of the far field, however, the beam strength is always greatest at the center of the beam. It diminishes as it spreads outwards. Okay, the beam in the when we talk about far field, the beam strength is greatest at the center of the beam and diminishes when it is spread outward. You can see how it is spreading outwards. So you can understand that the blue zone at the center of the beam, it is have the, you can say, strength. This blue zone in the center is having the strength. The beam spread is largely influenced by the frequency and the diameter of the transducer. For a flat piston source transducer, an approximation of the beam divergence angle at which the sound pressure is decreased by one half as compared to its value at the center line axis can be noted as sin theta is equal to 1.2 v upon df. So where theta is equals to the beam divergence angle from the center line to point where the signal is at half strength, and V is the sound velocity in the material, D is diameter of the transducer, and F is the frequency of the transducer. This formula you should understand. Now the types of scanning. The scanning also have a very you can say important relation when you talk about this word, this ultrasonic testing. They have classified the scanning into three types, like A, B, and C. Okay, and this you can say depending upon the data collected or depending upon the format of testing, they classify this into A, B, C, and C scanning. So let's discuss this types of scanning in our these PPTs. So the ultrasonic data, they can be collected and displayed in a number of different formats. Okay, while the three most common formats are known in the NDT, that is non-destructive and testing world, as A scan, B scan, and C scan representations. Okay, each representation mode provides a different way of looking at and evaluating the region of material being inspected. Okay, now the modern computerized ultrasonic scanning system can display data in all the three presentations from simultaneously. So now we will discuss about each scanning, that is A scanning, B scanning, and C scanning in detail. Okay, and the diagrams will help you to understand how A, B, C scanning is done independently, how it is presented and done independently. Okay, let's start with it. Now this is a slide diagram showing you A, B scanning representation. Okay, you can see how this there's a difference between A and B scan in this. So we will study this in the coming slides. Now A scan representation. Okay. So this A scan representation, this is displays the amount of received ultrasonic energy as a function of time. Okay, you can see this A scan presentation. You can see there is a time written on the horizontal axis and signal strength on the vertical axis. Okay, so they have divided them into 10 equal parts. Okay, and if you see that in the A scan, there are some terms written like IP, C, B, A, B, W. So each of this term has its importance. We will discuss now. Okay, after this. So they say that this A scan representation, they can presentation, sorry, A scan presentation, that displays the amount of received ultrasonic energy as a function of time. So the relative amount of received energy is plotted along the vertical axis and the elapsed time, which may be related to the travel distance within the material. Okay, the relative amount of received energy, what you energy you received, is plotted along the vertical axis. We have seen the signal strength. Okay, this is plotting along the vertical axis, and the elapsed time you can see on the horizontal axis. The elapsed time, which may be related to the travel distance in the material, is displayed along the horizontal axis. So clearly said that energy, received energy, or you can say the signal strength on the vertical axis, and the elapsed time, or you can say it is shown on the horizontal axis. So in this way they plot the scanning. And most instruments with an A scan displays allows the signal to be displayed in its natural radio frequency form, that is the RF radio frequency form, okay, as a fully rectified RF signal, or as rather the positive or negative half of the RF signal. Now in the A scan, relative discontinuity size can be estimated by comparing the signal amplitude obtained from an unknown reflector to that from a known reflector. Okay, the discontinuity. Okay, now in A scan, what they are doing, the discontinuity, they are estimating by comparing the signal amplitude from an unknown reflector to that of a known reflector. The reflected depth can be determined by the position of the signal on the horizontal screen. Okay, now A scan representation, sorry, A scan presentation, that is from the figure. The initial pulse generated by the transducer is represented by the signal IP. You can see the signal IP written there in the A scan presentation, which is near time 0. It is between 0 and 1 in the time, if you see 0. Okay. As the transducer is scanned along the surface of the part, four more signals are likely to appear at different times on the screen. When the transducer is scanning along the surface of the part, four more signals, okay, they are likely to appear at different times on the screen. So when the transducer is in a far left position, only the IP signal and the signal A, the sound energy reflected from the surface A, will be seen on the trace. Okay. Now as the transducer is scanned to the right, towards right it is going, a signal from the back wall BW will appear later in time, showing that the transducer has traveled farther to reach this surface. So when the transducer is overflow B, signal B will appear at a point on the time scale that is approximately halfway between the IP and the BW signal. Okay, it is only when the BW will appear on later on time, and then when the signal B is coming for the flow B, signal B is coming, that is approximately in middle of IP and BW signal. Okay, so since the IP signal corresponds to the front surface of the material, this IP is the front surface of the material. This indicates that the flow B is about halfway between the front and back surface of the sample. BW is back wall, IP is front surface. So they say that with this signal they are indicating that flow B is halfway from the front and the back surfaces. So when the transducer is moved over flow C, the signal C will appear earlier in time since the sound travel path is shorter. When the transducer is moved over flow C, the signal C will appear earlier in time since the sound travel path is shorter, and signal B will appear since sound will no longer be reflected from it. Okay, so this is how signal C will appear in time, and this is when signal B will disappear. Okay, then now B scan representation. This is also an important scan representation that you should know. Okay, now the B scan representation is a type of representation that is responsible for automated linear scanning system. Okay, where it shows a profile cross-sectional view of the test specimen. Now, in the B scan, the time of flight, that is the travel time of the sound wave, displayed along the vertical axis. You can see the time on that, and the linear position of the transducer is displayed on the horizontal axis. You see the scan distance shown there. So from the B scan, the depth of the reflector and the approximate linear dimensions in the scan direction can be determined. Okay, now how the B scan is helping? It is helping to find out the depth of the reflector. Okay, and the approximate linear dimension in the scan direction. You can easily find out the depth of the reflector and the linear dimension. It will help you in finding out that. So it is the typical produced by establishing a trigger gate on the A scan. So whenever the signal intensity is great enough to trigger the gate, a point is produced on the B scan. So the gate is triggered by the sound reflected from the back wall of the specimen and by small reflectors within the material. So in the B scan image shown, the line A is produced by as the we can say as the transducer is scanned over the reduced thickness portion of the specimen. Okay, so this is the way how the A line A is showing. Okay, so when the transducer moves to the right of this section, the back wall line BW is produced. Okay, you can see the BW on the in the scan distance right. Okay, when the transducer is over the floor B and C line, over the floors B and C, the lines that are similar to the length of the floors and at similar depth within the material are drawn on the B scan. Okay, so it should be noted that a limitation to the display technique, that is the reflectors, may be masked by larger reflectors near the surface. This is how B scanning is done. Now the C scanning representation is shown in this figure. You can see this figure how there is a C scan presentation, and I'll display sorry tell you later in this description. Okay, there. Now the C scan presentation is a type of presentation that is responsible for automated two-dimensional scanning system that provides a plan type view of the location and size of the test specimen features. You can see here the side view is there and the top view is there. So how it is displaying the, you can say, diagram. Okay, the diagram is here also. So the plane of the image is parallel to the scan pattern of the transducer. The C-scan presentations are typically produced with an automated data acquisition system. Now here the automation is coming, such as computer controlled immersion scanning system. Okay, what happens in C scanning? It is a type of a presentation that is possible for automated two-dimensional scanning system that provides a plan type view of the location, plan type view of the location and size of the test specimen features. Now here the size is also there with you, and you can say the location is also known to you. So this is advanced. So a data collection gate is established on the A scan, and the amplitude on the or the time of flight is signal is recorded at regular intervals as the transducer is scanned over the test piece. So the relative signal amplitude or the time of flight is displayed as a shade of gray or a color for each of the positions where data was recorded. Okay. The C-scan presentations provide us an image of the feature that reflects and scatter the sound within or the surface of the test piece. This is how they help you to find out the defect or something or some, you can say, location of the location of the discontinuity. Or application of ultrasonic testing, most commonly they are used for detection, maybe of cracks or inclusions or porosity or delamination or some erosion and corrosion, thickness gauging or assessment of bond integrity or estimation of grain size in metals or estimation of void content in composites and plastics. So these are some applications of ultrasonic testing. So let's start with the MCQs now because the MCQs are also need to be covered. Thank you. Okay, the first question for today's MCQ is that in the UT ultrasonic testing, these presentations are typically produced within an automated data acquisition system such as computer control immersion scan system. What do we call this? We call this as C-scan represent, C-scan presentations, and C-scan presentations. So in ultrasonic testing, force 50 does not produce a discrete reflection but scatter in the ultrasound in the range of directions, also resulting in transmission loss. So these transmission losses can be detected by mapping the transmitter signal. Okay, these transmission losses can be detected by mapping the transmission signal over the whole structure, known as we can call it as two transmission C scan. We just discussed. Okay, just in ultrasonic testing, in this section, the voltage signals produced by the transducer, which repeat the received ultrasonic pulses, are amplified. The amplified signal is available as an output for display or capture the signal processing. What do we call this? We call this as the receiver. We call it as the receiver. Thank you. When ultrasonic testing, it is the type of presentation that is possible for automated two-dimensional scanning system that provides a plan view, a plan type view of the location and size of the test specimen as a C-scan presentation that we just discussed now. In ultrasonic testing, this displays the air and makes it possible to get more sound energy into the test specimen so that a usable ultrasonic signal can be obtained. I repeat, understand. Ultrasonic testing, this displays the air and makes it possible to get more sound energy into the test specimen so that a usable ultrasonic signal can be obtained. It's called a couplant. Very simple and easy to understand couplant. In ultrasonic testing, besides its wide use in the engineering application, ultrasonic is also used in the medical field, such as for sonography. Okay. Now, the conversion of electrical pulses to mechanical vibration and the conversion of returned mechanical vibrations back to the electrical energy is the basis of ultrasonic testing. True or false? Well, the statement is true. Okay. When an electrical field is applied across the signal, the polarized molecules will align themselves with the electric field, causing the material to change dimensions. I repeat, understand it and then say anything. When electric field is applied across this material, we're applying an electric field. So when an electric field is applied across the material, the polarized molecules align themselves within the electric field, causing the material to change dimensions. In addition, a permanently polarized material such as quartz or barium titanate will produce an electric field when the material changes dimensions as a result of an imposed mechanical force. So you call this phenomenon as a piezoelectric phenomenon. True or false? So well, this phenomenon is known as piezoelectric effect. It is true in this case. Okay. So in ultrasonic testing, yes, displays the amount of received ultrasonic energy as a function of time. So the relative amount of received energy is plotted along the vertical axis and the elapsed time which may be related to the travel distance within the material. So it is displayed along the horizontal axis. So what do we call this? We call it as A-scan presentations. So ultrasonic testing is a type of presentation that is possible for automated linear scanning systems where it shows a profile cross-sectional view of the test specimen in this time of flight of the sound waves is displayed along the vertical axis and the linear position of the transducer displayed along the horizontal axis. What do we call this? We call it as a B-scan presentation. Here also we understand that now in A scan what is happening, it is displaying the amount of received ultrasonic energy as a function of time. So you can understand that this is displaying as a function of time. Okay, and when the plotting, what you are doing, the relative amount of received energy is plotted along the vertical axis, and the elapsed time, which may be related to the travel distance within the material, is spread along the horizontal axis. So here you're talking about this thing. So you can remember the A scan with the help of the axis, in which plotting is there. Okay, and in the B scan also you can understand that uh, what it is displaying. Okay, the time of flight of the sound wave is displayed along the vertical axis. So here the time is on the vertical axis, and the linear position of transducer is displayed along the horizontal axis. From this, you can easily understand the B-scan presentation. Okay, these are the references which you can refer and increase your knowledge. in this topic.